can you hear me? Hello, I'm Kazutaka Matsuda from Tohoku Universities. Here I'd like to explain that our embedding of invertible programming language that have bindings through a case study of a flipper programming language. So, why embedding of invertible programming language is challenging? So, this is because it has non-functional semantics. Here, non-functional semantics means that the meaning of a function is not a function from a meaning of A to meaning of B. Okay? Indeed, invertible programming language is has non-functional semantics. So, in a function in an invertible programming language runs both forward and backward. This means that meaning of a function in an invertible programming language is actually a pair of a function from some A to B and so B to A. So we also have some other example of programming language with non-functional semantics. So in bidirectional programming language, the meaning of a function is actually a length between A and B. So what we expect by using embedding? So since the programming language we want to embed have binders, we want to express such kind of binders in a nice way. That is, we want to use host functions to express such kind of binder. That is, we want to use higher order abstract syntax. So, for example, this is the tagless final style representation of simply typed lambda calculus. Here, binders in a lambda abstraction is represented by a Haskell function like this. Okay, let us consider the invertible programming language. So when we embed invertible programming language, we of course implement the inverse semantics of this. So since forward semantics, so it takes a user value environment and returns a value. So corresponding to this forward semantics and the backward semantics, that it takes a value and return the environment. Here comes an issue. So in the higher order abstract representation, there is no explicit environment. However, so we want to refer to environment in implementing inverse semantics. So the challenge is that how to deal with this gap. This is a completely different situation for in a usual function programming language that has a function semantics, because we can just interpret this E with just identity functor or monad or some applicative. So, but here we want to refer to environment to implement its inverse semantics. Fortunately, so we can use existing method. So unembedding. So unembedding is a transformation between the tagless final representation and the Doubler index term. So here is a tagless final representation of simply typed lambda calculus, and this is the Doubler index term representation of the simply typed lambda calculus. Unembedding is a transformation from the simply finally tagless type to the Doubler index term. So by this conversion, so we can access to the environment. So there's no problem on implementing inverse semantics that refers to the environment. Originally, embedding is designed to interconvert the user-friendly syntax and so program manipulation friendly semantics, that is finite tagless type and Doubler index term. So we find that unembedding technique is also useful for embedding a programming language that has non-functional semantics. So in this paper, so we embed Flipper by using unembedding. So Flipper is an invertible programming language that takes pretty printers and returns a corresponding person. So by embedding, so we want to achieve high interoperability with Haskell. That is, so we want to define manipulated in a Flipper by using Haskell data types And so we want to generate a flipper program by using Haskell programming. So here's our contributions. So we embed invertible programming language through an embedding technique. And so we redesigned the flipper programming language to enhance interoperability with Haskell. And so flipper equips with some fairly complex syntax restrictions and program manipulations. So we also discussed how to handle this kind of complex features of flipper in this embedding. Okay, so let us talk about the background of this research, the original flipper. This is the architecture of a flipper system. So it takes a pretty printer split in a core language and transforms it to a context-free grammars with action by using an inversion method. To this conversion possible, so the core language has a very strong syntactic restriction. So because that it always produces context-free grammars with action. But this, at the same time, that it is a bit hard to program with. So to overcome such kind of situations, flipper also comes with a surface programming language. So which the syntactic restrictions are fairly bit relaxed. And so these surface programs are converted to a core language by using partial evaluation and program fusion method. Okay, let us explain each language one by one. First of all, we explained about core language. Core language is actually a function programming language that has what was pretty primitive combinators as a primitive. So the core programming language has a restriction that it treats and password. Here is a syntax of the core language of a flipper. As you can see, the program consists of several rules, and each rule has this kind of form, and each expression is either what was combinators or function call. What is important here is that the argument of function call are all variables. This is the treeless restriction. The core language designed to be easy to invert, but it is hard to program with. So the flipper system comes with surface language. In a flipper surface language, so each function can have statically computed arguments, and so the treeless restriction is now relaxed. Actually, this is actually relaxed treeless restriction. So each function has a tiers, and the function in the lower tier can be treated as primitive in a higher tier. So, but please do not read this, because that's we do not use surface language in this embedding. So anyway, what is important here is that the treeless restriction is indeed relaxed. Actually, this argument of this function is not a variable. Anyways, let us explain a bit more about pretty printing. So here, pretty printing is that printing AST nicely depending on the screen width. So here we explain this program a bit. So actually, this is a printer or AST that consists only of subtraction operators and constant one. Okay, so this is a pretty printer, the entry point of this pretty printer. For now, we ignore this function. So it just calls AUX with the same parameters. So what AUX function do? So if the input is a constant one, it just output the string one. So for that, if the input is subtraction operator, so we just go with just a smart choice operator that smartly chooses a horizontal layer versus vertical layout. And so this function parents if the put parents is if this is true. And we just recursively call the PPR function with false for the left argument, so because that subtraction is a left associative operator. And so we put the nest, this increases the current indentation level. So here, line is just a new line character, but it has some different behavior under the group. Under the group, so line will be printed so as a single parameter if there is enough space, enough horizontal space. If there is no such kind of enough horizontal space, the line will be rendered as a new line character with appropriate amount of indentation. After this, we put the minus sign and together with a single space, and then we call the PPR function recursively with the right child. So thanks to this pretty printing function, this AST can be printed as this or this, depending on the screen width. So what is important here is that this program, this is actually invertible programming language. This means that this program also runs backward. So in a backward, so this function not only passes this kind of pretty printed output, it also passes some ugly output. This is actually this is made possible by these kind of things. So, for example, so many parentheses indicate that we can put many parentheses as at this point. So here, this is not a Wallace combinator, but input. We use this combinator to express such kind of additional or information so used in the parsing phase. Anyway, this is the behavior of original flipper language. So why do we want to embed flipper? Because that we want to enhance the interoperability with Haskell. Instead of defining the data types in the flipper language, so we want to pretty print the user-defined Haskell data types with type checking. Also, we want to replace the surface language with programming in Haskell, because the surface language comes with fairly complex syntax restriction, and so we have to also it will be converted to a core language with some fairly complex program transformation, that is partial evaluation and fusion. We want to avoid such kind of complex implementation. Also, we prefer type-based restriction rather than the syntax restriction for treelessness restriction. Okay, this is the existing work. So now we have explained how we embed this flipper by using embedding. So we first talk about the redesign of a flipper. So the interoperable flipper is actually the redesign of a flipper core language. So it has a greater interoperability with Haskell. Specifically, it allows pretty printers to handle the user-defined data types in Haskell. Also, it uses lambdas instead of a global function definition, so which is good for embedding, but it's still faster than the trees. Let us explain the syntax of the interoperable flipper. So here, expression is either lambda abstraction and function application, and here is what was pretty printing combinators. And so what is important here is that pattern matching functionality in the original flipper is divided into the three language constructs. The most important one is a case expression. Here, phi I is a partial injection which can be represented by a Haskell data type like this. So this arrow notation is very close to the view pattern in Haskell. So in a forward execution, this tries to apply compute phi I x, and if it returns just something, so we bind it to xi and then execute ai. And so if it returns nothing, we just try other branch. And other left branch is to decompose that Haskell level product by using Haskell level products. So Also, other important thing is that the language is still faster than treeless. So you can see that so we only allow variable in some specific position. For example, so the argument of function call, function application, and this scrutiny position of pattern matching. So this is still a treeless programming language. So having this defined, the embedding is rather easy. We just prepare the type class so representing its syntax. So here, so the flipper it takes two type variables, A and E. So A representing argument is corresponding to variables in this syntax definition, and E representing expressions corresponding to expressions in this syntax definition. So we need to split the type variable because that's to enforce treelessness. So here, this ABS corresponding to a lambda abstraction, and APP corresponding to this application, and case corresponding to this case expression, and unit corresponding to these forms of let, and ampere corresponding to these forms of let, and text is one of Wadsworth pretty printing combinators, and so this doc is representing a pretty printed result. Okay, so now we define its forward and backward semantics. Defining the forward semantics is rather easy because that we just use identity function for A and E. So yeah, this is very straightforward. So by using this instance declaration, we can define a pretty printing interpretation of a flipper function. If we have a flipper function that takes sigma and returns doc, we have some pretty printer that takes sigma and returns doc. But parsing interpretation is much more interesting and challenging. So this is because that in the definition, so we want to define its inverse semantics as in a way that the term in context of type doc will be interpreted as some grammar that of which return type is gamma. So that is we want to refer environment in implementation. So to do so, we use an embedding to handle such kind of gamma. So thanks to an embedding, so we can implement parsing interpretation of flipper function. So this means that we have some a function from a sigma to doc or pretty printers or for sigma type in flipper, so we can interpret it as some grammar that returning sigma type. So please see our paper for detail. So this is the basic idea. So let us explain much about the handling recursion. So we want to handle recursion explicitly because because parsing algorithms treats them explicitly. For example, case parsing and early parsing and many other kinds of parsing algorithms treat recursion explicitly. And also we want to note that flipper can generate left recursions and unusual parser combinators and Haskell level recursion do not terminate for left recursive grammars. So we want to note that we want to handle mutual recursion because that it is quite usual to define a mutual recursive pretty printers. Also, and we want to use Haskell language support as possible. That is, we want to define recursive function recursive way. So fortunately, we have a solution. So by using existing techniques, we just use marking for explicit laziness. Actually, so we extend that type class flipper E to a flipper D. For this D stands for declaration. So that has a mark method that takes flipper expression and and returns it enclosing with some monad. Thanks to this mark method, so we can define a recursive function expression we can define recursive function by using recursive do notation like this. One can think that this mark is something similar to lazy in camel, so this is explicit laziness. So we can do since this is explicit, we can obtain some recursive structure explicitly. So we also so this is the basic kind of recursion. So we also have some derived combinators. So one is some pattern-like combinators, which allows us to write case expression much more natural way, and also we have some better ways to define definitions. So instead of directly writing a mark, so we can write this kind of way. So we do not need ABS and up, and also that by using this function, so a function can take a statically computed parameter. Okay, so this actually, so thanks to these techniques, so we can write programs like this. This is the same program flags. This is the original. This is the same program as this program. So this is the original flipper program I explained before. So as you can see, that the program becomes fairly complicated. So, but I think that still this is manageably complex, because we can define the guess function by using Haskell level numbers and like as this, and also this complexity also deserves for the advantage, so such that we can define the ASTs by using Haskell data types, and so now the pretty printing function is type checked by using Haskell. Okay, our paper also includes some local functions. This is the impulse of a mark and corresponding to a left leg, and so which allows us to define pretty printing combinators, derived pretty printing combinator like this. And also we discuss some implementation issues, mostly for efficiency. And our paper also discuss some much more involved examples. Okay, let us explain some related work. There is some existing invertible bidirectional language in Haskell, but they are basically all combinator based. That is, there are no binders. Also, that our applicative range is also similar to has some similar spirits, and so in applicative lens, so this has some conversion from lenses to functions. So it has some lift functions that convert left to lens to this polymorphic function, and this also provide unlift that takes polymorphic function to lens. So this is based on some Yoneda embedding. So, but this is only for functions and not scalable to other kind of binders like a case expression. So this problem is actually addressed in our recent work, but this is a standalone language. But this means that this language also benefits from our technique. Also, there is another kind of pretty printing combinators. I guess that Fuge's, so some of you also have used Fuge's combinators, and so there's also Bernardi's combinators. So there's no problem on the flipper to treat this kind of combinators, but we have not implemented these kind of things. Anyway, let us conclude this talk. We embed invertible programming languages that have binders by using an embedding technique. Through a case study, we explained this through a case study of a flipper case. And so thanks to this embedding, so the flipper now has a greater interoperability with Haskell. And so this embedding-based implementation is scales to explicit recursion. So, but there is a disclaimer. So we use some unproved conjecture for mark and local. So this is less for future work. Okay, thank you.
phrase the stuff about reversible computation in terms of probability of compiling categories. So you boil down to a category that's got reversibility included in it.
So your question is that, so can we explain some reversible computation in some category and?
Well, yeah, and then that will give you the embedding from a Haskell surface language down to sentence and origin CCC.
So usually reversible programming language is not a CCC, so.
I think I can say two words. So what Connor presented is not appropriate because you have copying in diagonal operator and erasure. But instead of Cartesian category, you can use monoidal category, and that corresponds in some sense. You need more, but in that you can express reversible computations. Also, there are other reversible programming languages, and well, that's the one. Yeah. You can go.
I guess it is possible, but it takes some time to for precise answers.
I just wonder if it's possible to define a function that's valid as a pretty printer in the language, but that doesn't work as a possible. Is it possible to do that?
What do you mean by doesn't work for parsing?
I just wonder what's the soundness of this?
I'm sorry?
What's the soundness of this embedding?
Oh, soundness is that, so soundness is that whether nose comes right in. Soundness is that, soundness is that the pretty printed result is always possible and returns the same AST.
I understand it's possible with Flipper, right? But with this embedding, you transfer to this.
Yeah, actually, this is actually proved in Flipper, but we do not do such kind of certification of the embedding. We just made as what Flipper did, and believe that this also holds in the embedded version.
So when you parse and pretty print, in the case that you had here with the reverse arrow, you could get something else, right? So you lose those parentheses, for example. So it's not really inverse, but more like an adjunction. Also, another example that if you had some comments, if you parse them, print, you could lose the comments. Is that possible? Preserve those comments or those parentheses in some auxiliary data structure.
So actually, this you are right that this can lose. So if we start from this direction, so if we pass this in and we get either this and this, so this means that we lose parentheses or comment structure. So actually, this makes that things to be from some invertible things to bidirectional things. So it is still open because that we use a very complex inverse computation algorithm, or we are just using existing parsing algorithm. And so how to interact this kind of thing with bidirectional touch system is still challenging in my understanding.
Thank you. So I have a question,
Okay.
which is similar to Alan's question. So my understanding is the reason you used embedding is because it wasn't obvious how you could just kind of give a direct interpretation of the higher order abstract syntax. Did you try? Did you try to come up with some other direct interpretation? Because the way that the reason we used embedding originally was partly because it allows you to do much more ad hoc kinds of optimizations on code, because you just have direct access to the syntax.
Yes.
Did you try something first to get started?
Actually, so it is, we just implement the semantics, semantics, but actually, sorry, and okay. Which we basically just implement the semantics, but it equips some program transformation after we get grammar. So we do not do some much complex thing at this phase, but we after this phase.
Yeah, I was just wondering whether you could align the whole embedding. Yes, you.
So indeed that we do not construct AST, so AST or some Dura index term derived, so because we just want to implement some semantics. So actually we do not involve any deep embedding. So maybe this is some simple programming language that without comes with optimization and this kind of thing. So what we can do is it's sufficient to do with something obtained in a grammar. Maybe this has become possible for much more complex language, but I'm not so sure.
Okay, thank you.